All right, guys, so this is the last video that you're going to have to watch, so congratulations on that. We are reviewing for the final exam, so the review I just have laid out here, and I've drawn a lot of the pictures to start. So it says, number one, a golf ball is hit with a velocity of 60 meters per second and an angle of 35 degrees. So again, we need to identify what things are. So the initial velocity would be 60. The angle is theta. So as soon as you have theta and VI, in order to work with what we need to do with the constant accelerated equations with like the y and the x directions, you're going to have to do some trig in the beginning. So whenever you see theta, that's your indication that, okay, I got to do trig before I can just start plugging in numbers into our chart. So I'm just filling out the chart with the initial and final velocities, the change in y, gravity, and time. So that's g. And then we got the x direction, which is the horizontal displacement, the initial velocity in the x, which is constant, so that's why you don't need an acceleration or a final velocity in the x, and then the time here. So to get the VIX, you would do VI cosine of theta. So when you plug into that, it's going to look like 60 times the cosine of 35 degrees. And when I put that in my calculator, I got like 49.15. And again, that's the x direction, that's meters per second. That's the x direction, so that's going to go right here. So 49.15 goes in that box there. For VIY, make this a little smaller. There we go. VIY is really similar. Instead of using cosine, you're going to use sine. So it'd be VI sine of theta. And it would be 60 times the sine of 35 degrees. Again, make sure your calculator is in degree mode. Otherwise, it'll give you the wrong value. And when you put that in your calculator, you should get something like 34.41. So if you would have rounded to 49.2 or 34.4, that's fine. I just went out another digit. It doesn't really make a difference. So that goes in here, the 34.41. All right, so those are just like initial starting. Whenever you have theta, you got to do the trig. Gravity we know is negative 9.8. And I think that's all the numbers that they tell us. So it says that what is the maximum height the ball reaches. So we're at the maximum height, so we're looking for that height. So that's going to be a question mark. And this is the apex. So if we're using the apex here, we should know one more idea. So when it reaches the highest point, the final velocity is 0. So once we have that filled in, we have 3 out of 5. We're good to solve, and we can start using our formulas. So the first formula that I'm going to use for part A here is the VF squared equals VI squared plus 2G delta Y. And I left the little subscripts out, but these are just Y components because, again, you got to work with all the Y stuff, all the Y ideas, and then all the X ideas another time. So we know this is 0 squared equals the Y component, which is the 34.41. Squared plus 2 times negative 9.8 delta y. And I'm going to take this term to the other side through addition. So this is negative 19.6 delta y. When I take it to the side, it becomes a positive 19.6 delta y. It's 19.6 because 2 times 9.8 is 19.6, and it's negative here, so I take it to the other side, it's positive. So that's the left side of the equation. The right side of the equation, when I square 34.41, I got 1,184.05 or so. I'm rounding a little bit here, but it's close enough. And then you divide through by the 19.6. So when you do that, you get delta y, and I got my y component to be 60.41 meters. So it goes pretty high in the air. So coming back to part B, it says how much time does it take? So we're looking for, that was part A, we got that. And we can solve for part B, again, with any equation, because we're looking for all 4 of these ideas, so I could plug that in. for delta y. The one that I used for part B is the VFY equals VIY plus GT equation. So we're looking for T. So again, the final velocity is 0. The initial velocity is that 34.41. And then I got negative 9.8 delta T. Again, I'm going to make things positive, so I'm taking this term over to the other side. So it's negative on the right, it's going to be positive on the left. So 9.8 delta T equals 34.41. And then it's just dividing through by gravity on both sides. Again, just taking you through all the algebra. So when that happens, you get delta T, and this is only the time going up. So just to be clear, this is just the time to go from the lowest point up to this highest point up here at the apex. So when you do that, you get around 3.5 seconds. So it's 3.51 seconds. And that is actually what they're asking for in part B. They want to know how long does it take to reach the highest point. So that's 3.51 seconds going this way, going up. It also is going to take the same amount of time coming down. So for part C, it actually wants to know what's the horizontal displacement, the entire horizontal displacement, which is delta x. And there's only one equation for the horizontal, so that's VIX times T. If we want the total displacement horizontally, we want the total time. So as we were talking about just a second ago, we're going to take this and double it to get the total time. So if I take 3.51 and double it, it becomes 7.02. And then it's just multiplying those two numbers together. So it would be 49.15 for the velocity in the x. That was from our first kind of calculation there. And then we're going to multiply that by the entire time that it's moving up and down. So that's 7.02. And that's already set up to solve for delta x, so I don't have to do any algebra. I just got to plug it in the calculator. And you should get a horizontal distance of 300. That's supposed to be a 3. Let me try to make that better. 345 meters or so. It's like 0.003 or 0.033 is what I got. So, so those are the first three answers here for our projectile motion problem. This one is launched at an angle. The next one is launched horizontally. So we have a ball rolling off of a table horizontally, and it's going to go through projectile motion. The speed initial here is 5, so that's VI. And since it's horizontal, it's VIX. So we know VIX is 5, VIY is 0 because it's not going up or down. It tells us the height of the counter, so this is like 1.5 meters up above the ground. And then it says how long is the ball in the air, how far from the edge of the table does it land, what's this should say ball, what's the ball's velocity in the vertical direction when it hits the ground, and then what angle does the ball make with the horizontal as it hits. So again, we're going to set up our tables. So if we get through our y and our x tables, that's kind of where you start always with kinematics. So we got change in y, VIY, VFY, G delta t, and then for the x, it's delta x and the velocity initial on the x and the time that it's moving for. So we can take VIX and put in 5 here, so that's okay. For gravity, it's always negative 9.8 unless we're on some other planet, which we're not. And then our VIY is 0 because it's going horizontally only, so it's not going up or down. So we have some other things. And then 1.5 meters, that's the change in height. Just to be clear, a lot of people put 1.5 here for delta y. That would mean it's, if you have this as positive, it's going up 1.5, and that's not what it's doing. It's not shooting upward. It's falling off the table and moving down. So make sure you put the negative in here. We got 3 out of 5, so we're good to solve. We're looking for time, so I'm going to put a question mark there, and I don't care about VFY. So for part A, the equation that you want is this one. So delta y equals VIY delta t plus 1/2 g delta t squared. Hopefully, again, this selection process of picking the right equation has become easy. Remember, you're looking for 3 out of 5. You put the question mark, and then the box that is empty is the one that the variable that you don't want in the equation, which will get you that one. So plugging in, I got negative 1.5. The first term goes away because VI is 0, so that whole first term goes away. 1/2 times negative 9.8 is negative 4.9. So I'm just doing this in one step. And then delta t squared. You're going to divide by negative 4.9 on both sides. That will get you a positive number, which is good because eventually, so those cancel. You're going to have to take a square root to get to just t, and we don't want a negative number because you can't take the square root of a negative number. So for delta t, for this one, I got 0.553 seconds. So that is our time. So that can go in here. It can also go in here because it's the same time. So it's falling as it's moving horizontally. It's not going up and coming back down. So it's just, that's our total time. For part B, it says, how far from the edge of the table does it land? So for part B, you are looking for delta x, which again is just the only equation for the x direction is VIX delta t. And you're going to plug into that. So you got 5, and you're going to multiply that by the 0.553. That's supposed to be a 5 there. There we go. So that's delta x, and when you do that, you get delta x is equal to, it's a little over 2.5, so 2.765 meters is the horizontal displacement. So that's that one. For part C, it wants to know what's the book's velocity in the vertical direction when it's running into the ground. So for part C, we're looking for VFY. And we're just looking for the y component, so that's okay. We would expect it's moving downward here, so VFY should be negative. And I'm just using any equation that I want, but this is the simplest one, I think, for what we need. So, because we have 4 out of the 5 variables. So VIY is 0, because it's not throwing our up or down. VFY is what we're looking for, and it's really just this negative 9.8 times the time, which is the 0.553. So for VFY, you should get something like negative 5 I'll just call it 42. It's rounded slightly, but that's okay. That's meters per second. So that is that answer to part C. And then finally for part D here, it wants to know what angle does it make as it hits the ground. So we just found VFY. We know the horizontal component because that's given to us as 5. So we got 5 going across that way for the x. This is the y we just found. And we're looking for the angle. So a lot of times in previous problems, we would solve for like the overall velocity and the angle. We're just looking for the angle here. So we're just looking for theta. So with theta, if I redraw this triangle again with some numbers in it. So we have 5 going across. To the right, that's the horizontal piece. And I have 5.42 negative going down. And we want this angle theta. So we don't care about the hypotenuse, we're just looking for theta. So when we do that, we would use the opposite over the adjacent, which is the tan. So the tan of theta would be equal to the opposite side, which is negative 5.42, over the adjacent side, which is 5. And when you put that in your calculator, again, you got to get theta to the other side, so it'd be the inverse tan. Again, just taking you through all the steps of the values that we put in, so 5.42 over 5. And when you do that, you get theta is equal to something like 47.3 degrees. And you want to be specific as to where it's going. It's going down, so that's below. And you can just use either the positive x, below the positive x is going to the right, or you can say below horizontal. Either one of those is okay for that answer. All right, so that's the first 2 problems. I'm going to pause there because those are the 2 that deal with projectile motion, and then we're going to jump into force. All right, so our next problem, number 3, says an 80-kilogram object is pushed to the right with a force of 500 newtons, and it tells us the coefficient of friction. So this is U. This is a pushing force, so I can kind of put that as going to be one of my forces. So I'll just say the push. And the pushing force, it looks like it's going to the right. So I got the pushing force. 80 kilograms, that's the mass. It says to draw a free body diagram, so I started to do that here if this dot represents the box. Let me pause a second and I'll have the other arrows in there so you can look at it. So I've drawn in the other forces. So we had the push going to the right as described here, push to the right with 500 newtons. Gravity, normal force that are going to be there. We recognize that they're going to balance out because there aren't any other forces up and down, and this box isn't going to just fall through the surface. And then it tells us a coefficient of kinetic friction, so that means there's going to be kinetic frictional force while this thing moves, so that's going to go the opposite way. So I'm just filling in the table with the ideas, with the items from your free body diagram. So we got those 4 forces here: push, gravity, normal force, kinetic friction, and then the net force, which is when you put them all together. It's been a little while since maybe we've used a table, but it's the same idea as what we had before. So you're just going to go through and put in all the plus minus zeros for the directional stuff. So the push is going to the right, so that's positive in the x, and it's not going in the y, it's 0. Gravity doesn't go in the x direction, gravity goes downward, so that's negative in the y. Normal force is not going in the x direction, so that's 0, and it's going up in the y. And then the friction force is going negative in the x, and it's not going in the y, so that's 0. The y component balances out, so we know that the net force in the y is also 0. So I can put in 500 for the x because they told us that. And then every other idea we're going to get here, we're going to get through a formula or some sort of concept that makes it work. So let's just do gravity first because most people remember the gravity equation. That's just m times g. So it's going to be 80 times 9.8. I forgot a 0. 80 times 9.8, not 8. So when you do 80 times 9.8, you end up with a fairly large number. You get 784 newtons. So that goes in here. That's also going to be the normal force because those are balancing out. All right, so looking through, we've drawn a free body diagram. We just calculated the weight, we calculated the normal force. So that one step kind of got us several boxes, all right, because those have to balance out to get to 0. The force of kinetic friction, that's letter D here. So the kinetic friction equation is the fun equation. So the coefficient of kinetic friction times the normal force. And we have both those numbers, so that shouldn't be a big deal. So 0.14 times the 784. And if you multiply those out, that gives you a value of 109.76. So 109.76 is going to go in this box. And then we've calculated the force of kinetic friction. The last thing, or last couple things you can do, you can find the normal force or the net force. So you're just going to add. So we add these columns. So 500 minus 109.76 gets you 390.24. And that's a positive because that's the net force. Oh, these are all newtons, so I could put newtons in all these boxes here because that's the unit for force. So that's the net force. And then finally for F, we're going to do Newton's second law, which is the net force is equal to the mass times the acceleration. So we got the 390.24 here, and that's equal to m, which is 80 times a. So we're going to divide through by 80 on both sides. And if you do that, sorry, my cat is squawking, you'll get something like 4.878. You could round that to 4.88 if you wanted. That's meters per second squared because it's an acceleration, and it goes in the same direction as the net force, which is going to the right. So that is your answer to the last part of this question. I'm going to stop the video here and segment it a little bit. The next one we're going to get into deals with energy and momentum. So we've done kind of the first 2 units with kinematics and Newton's laws and force.